So let me start with the motivation. So what is the connection between data and metric spaces? So the way we usually handle data today is the following. We start with a bunch of real-world objects, and they can be images or text documents or time series data or anything at all. And the first thing that we do, almost without exception, is first to embed them into a high-dimensional space. So we take every image, or every object, suppose it's an image, we represent it by a long list of numbers that we call the feature vector, and we treat this vector as a point in R to the D. And this is a classic approach. There are some very old papers showing how to construct good high-dimensional representations of different types of data, but recently it received an even further spur by the discovery that neural networks are very good at this. So they can produce very high-quality representations of different types of data. For our purposes, it's not going to matter. What matters is that we can treat our data set as a set of points in R to the D. Now, what does that give us? The ability to quantify and measure distances between data objects. So for example, as humans, we have some notion of what it means that two images are similar or dissimilar, but we cannot necessarily quantify it. So this is a way to quantify it. I can measure exactly the Euclidean distance between the representation of two images in this space. And if the embedding is meaningful, then if the images are similar to a human, hopefully they're going to be close to each other in this space. And once we have our way to measure distances, we can perform a variety of computations. Some common examples are nearest neighbor search, clustering, density estimation, and there are many more. All of them are problems defined on the distances. And for this talk, I am mainly going to concentrate on nearest neighbor search, which is the following problem. We get a new image, and we want to find the closest image to it in the dataset. And if, for example, here X is the nearest image to my new image, my red point. So if X is an image of the Eiffel Tower, maybe my new point is also an image of the Eiffel Tower, and I learned something about my new image from the data. This is called the nearest neighbor classifier. So this is the overall pipeline. It is widely used. It gives good results. But of course, there are scalability issues. So datasets become larger and larger. The dimension also needs to be large to get good accuracy, and this burdens computational resources. So one way to deal with this is by efficient representations of the metric data. What does that mean? It means that instead of directly feeding our points into the algorithm, we are going to introduce an intermediate step where we first compress the data. So we produce some smaller representation of it, and we feed that into our algorithm. And because those algorithms that we run are based only on the distances, then as long as the compressed representation preserves the distances, we are going to get the same result that we were going to get anyway. And if the compression is lossy and there is some approximation, we are going to get approximately the same results, which for most cases is fine. So why would compression lead us to faster algorithms? There are a few reasons. So first, on the most basic level, if your data set is smaller, then hopefully scanning it takes less time. And especially for nearest neighbor search, many algorithms are based on linear scan, at least as a subroutine. And there are more specific reasons. So for example, today, a lot of computation is based on GPUs, graphical processing units. These are pieces of hardware that are very good at performing some operations very fast, but they have limited memory. So if you could squeeze your data so it fits on one of those GPUs, maybe you can do things faster. And this was demonstrated nicely recently in Facebook research in a paper that by now has turned into an open source library for nearest neighbor search. What they did is they took a data set of billions of images, they compressed it so as to preserve the Euclidean distances, and then they fit it on a GPU, and they could run nearest neighbor search queries by exhaustive search very quickly on this huge data set. So I want to start with a question, which is maybe the most fundamental question you can ask in this space of efficient metric representations. What is the smallest space you need to represent your metric space? So a bit more specifically, we are given endpoints in R to the D. How much space do we need to represent all the Euclidean distances between all those pairs up to a given precision of 1 plus minus epsilon? So let me define the model exactly. It's going to be a two-stage model. In the first stage, we get our data set, x1 to xn, in R to the D. And our goal is to produce a small size representation of it that I'm going to call the sketch. And in the second stage, which is the query stage, we no longer have access to the original points. We only have access to our sketch. We get two identifiers of points, I and j, and we need to report a 1 plus minus epsilon approximation of the distance from xi to xj. And we need to do this for every pair ij. And our goal is going to be to minimize the size of the sketch, or in other words, to get optimal compression. The classical approach to this problem is goes through dimension reduction. So a very central and famous theorem by Johnson and Strauss tells us that no matter what the original dimension of the points was, we can always reduce it to log n over epsilon squared. And this is a pretty dramatic statement because we know that if we wanted to represent the distances exactly, we might have needed in the worst case n-1 dimensions. But this theorem tells you that if you are okay with this small error of epsilon, then you can improve the dimension exponentially. One way to think about it is to visualize our data set as a data matrix, where each row is a point, so we have n rows, and each column is a dimension, so we have d columns. And this theorem tells us that we can replace it with a skinnier data matrix that has less columns, such that the distance between every pair of rows is approximately preserved. So this is already a form of compression because this skinnier matrix is smaller. How much space do we need to represent it exactly? This is not an obvious question, is it? Maybe it sounds. You do need to do some work to discretize this dimension reduction theorem, but it has been done in many works actually. And the upshot of all of them is that if, for example, your coordinates are polynomially bounded, which means that each number can be represented by log n bits, then the total space you need is the number of bits per coordinate, which is log n, times the number of coordinates, which is log n over epsilon squared, for a total of log squared n over epsilon squared bits per point. So this is what you get from dimension reduction. And the question is, of course, is this optimal or can we do better? So this is a little bit of a tricky question because we know that the Johnson-Liederschaft theorem is tight. So even though this is a recent result, we knew for a while before that it's essentially tight. This lower bound here is up to log 1 over epsilon. But this tightness is for dimension reduction. So it means you cannot make the matrix any skinnier. You cannot use less dimensions or less coordinates. But it doesn't mean that maybe you can do something else, use a completely different data structure, whatever you want, not a skinnier matrix, and improve the space bound. And this is what we are going to do. And I should mention that this approach of going one step beyond dimension reduction and using more general sketches is actually very common in practice, and it's a very fruitful line of research in the applied communities of computer science. There is some list of references here. I hope you can at least see that every big venue in machine learning, data analysis, computer vision is represented here. So this approach works, it gives you good results in practice, but all of these algorithms here are heuristics. So before our work, it was not known whether you can get something out of it in the worst case asymptotic principled sense, and this is the gap that we are going to close. So let me state what is maybe the most representative theorem of this thesis, and most of the other things I'm going to talk about are going to branch out of it. So the optimal compression size for Euclidean metrics is log n over epsilon squared bits per point. This is both sufficient and necessary, where again, n is the number of points, and the 1 plus minus epsilon is the approximation of each distance. And let's compare this again to dimension reduction. So this is a bit subtle. Dimension reduction told us that we can use the same number of coordinates, but each coordinates take some number of bits, which is super constant. So for example, if the coordinates were polynomially bounded, we needed log squared n over epsilon squared bits per point. And more generally, we don't really need this assumption about the bound on the coordinates. I'm just going to make it for the slide for simplicity, but just for a second, let me state that full bound. So in the most general case, your metric space has aspect ratio phi. This means that the distances range from, for example, 1 to 5. And then the optimal bound is log n over epsilon squared plus log 5 versus what you get from dimension reduction, which is log n over epsilon squared times log 5. And the upshot of all this is that indeed metric compression is possible beyond dimension reduction in a worst case asymptotic sense. So this is one result. Let me state another result. So this is a little bit of a detour, but I want to mention it. So the same question that I posed about Euclidean metric spaces, we can ask about any family of metric spaces. What is the minimum space you need to represent it? And in particular, you can ask it about general metric spaces. So any set of points with distances that satisfy the triangle inequality. And here we also get a tight bound, and it turns out to be n squared times log 1 over epsilon for the whole metric space. And this ties to a line of work in theoretical computer science called distance oracles. So the distance oracle problem is exactly the same problem. The only difference is that classically they cared about a different regime of distortion or approximation, specifically when the approximation is at least 3. The reason being that in this range you can get subquadratic sketch size. So you can get n to the power which is less than 2. For less than 3, this is not possible. It's pretty easy to show. But in the 1 plus minus epsilon regime, which is what we care about, the best thing that was known before our work was just naive rounding. So you take each distance, you round it to its nearest power of 1 plus minus epsilon, or 1 plus epsilon. This clearly gives you a correct sketch, and it has this size if you compute it. For example, if you want a 2 approximation of each distance, then we get the tight bound of n squared bits up to a constant, whereas the previous one was n squared log n. And the reason I mentioned all this is not so much that I think that this log n is absolutely crucial. It's more because we got this result for free. So the same algorithm that gives us the optimal bound in the Euclidean case, and that I'm going to show you in a few minutes, it also gives you the optimal bound in the general metric case, which is a pretty different case. So I just thought this was interesting. And finally, the last aspect of the results that I want to talk about is what happens when you have new query points. So the way I presented the model now, we got our data points in the preprocessing stage, and we only needed to recover distances between pair of points that we had known in advance, that we had access to during the sketching phase. But this is not quite how things look in practice usually. The way things look in practice, especially in nearest neighbor search, is that you get in the query stage a completely new point y that you didn't know about during the sketching stage, and you still need to use the sketch to estimate distances to that point. So here you can consider two types of queries. One is the same distance query from before. We need to report a 1 plus minus epsilon approximation of the distance from y to each point in the data set. And the second type of queries is the nearest neighbor query. So we need to report an identifier of a point, which is approximately the closest point to y in the data set. So for example, here, this black point is the closest point to y, but I'm allowed to return this xi star because it's almost as close as the nearest neighbor, or namely, it's an approximate nearest neighbor. And let me just make the point that distance queries are in general at least as difficult as nearest neighbor queries, because if I have all the distances, I just take the minimum, and that's my nearest neighbor. Whereas this also holds under approximation, whereas the opposite is not true. If I know the nearest neighbor, I cannot necessarily tell you all of the distances. Okay, and again, our goal is going to be to minimize the size of the sketch. So let me go over previous results and our results in this setting. So all of the works I mentioned earlier about discretized dimension reduction, and there are many of them, they all automatically have query support. So they can handle polynomially many queries for free with the same size of log squared n bits per point. And recently this has gotten even better. So a very recent line of work known as terminal dimension reduction showed that you don't even need this limitation. This worked for any number of queries. And on the other hand, there is a lower bound. So in 2013, it was shown that log squared n bits are actually necessary if you want to estimate distances to new query points. And this lower bound is not on the dimension. This is a space lower bound. It means that no sketch, any sketch cannot break this lower bound of log squared n bits. So on the surface, it might look like the issue is closed. The best you can do is dimension reduction, and this is the optimal sketch size. But of course, it's not true because this lower bound has assumptions. And the most obvious of which is that the number of queries here needs to be at least as large as the number of data points. And I want to argue that the complement setting, when the number of queries is smaller, is at least as interesting, if not more, for two reasons. So one, from a conceptual point of view, it is maybe more natural to ask what happens to a single query point before you jump to n query points. And the second is that if you think about how things look in practice or how we usually think about them, then usually the query set is smaller, at least in the most famous standard benchmark datasets in machine learning. It is the case that the query set is smaller than the dataset by at least an order of magnitude. So think about MNIST, SIFT, 20 news groups. Your favorite dataset probably has this property. So let's see what are our results in this regime. So this is the theorem I already mentioned. If you don't have any query points to deal with, then you can do log n bits per point. And when we start adding query points, we get a smooth interpolation between our log n bounds without query points to log squared n bounds that handles any number of query points by dimension reduction. And the total size is log n times log u bits per point if you have n data points and q query points. And this is also tight. So even if you have a constant number of queries, you still need only log n bits per point, which is quadratically better than dimension reduction. So this closes the issue for distance queries. If your query set is bigger than your data set, then dimension reduction is the best you can do. Otherwise, you need to use more generic sketches beyond dimension reduction to get the optimal bound. There is still one missing line in this table, and the reason is that these two lower bounds have another assumption, which is that we need to answer distance queries. And as I said, nearest neighbor queries are potentially easier, and this is indeed the case. So our final result here is that if you only need to report approximate nearest neighbors, then the number of bits per point you need is log n plus log q. So even if you have polynomially many queries, you still need only log n bits per point, which is quadratically better than dimension reduction. And this is the smallest known data structure for high-dimensional Euclidean approximate nearest neighbor search. Okay, so this is all I wanted to say about the results, and I'm going to move on to describing the algorithm, unless there are any questions meanwhile about the introduction. Okay, so I'm going to move on, and feel free to ask me questions along the way. Okay, so let me describe the compression algorithm. The overall philosophy, so-called, of the algorithm is going to be to store each point as the displacement from a nearby point. And if you think about it, this is very natural, because usually when we think about, when we tell each other where things are or how to get to places, we describe locations relative to other locations that we already know. But if you think about dimension reduction, it doesn't do that. Dimension reduction tells you where each point is in the space in an absolute sense. And this is where we are going to get a improvement. So concretely, suppose we have these 2 points, x1 and y1, and the distance between them is r. We are going to define a surrogate for each point. And the surrogate is going to be a point which is an approximation of the original point, but easier to store. So x1 is just going to be its own surrogate. And to define the surrogate of x2, I'm going to compute the displacement, the difference from x2 to the previous point, x1. I'm going to round it with an epsilon net, and I'm going to add it back to the previous surrogate to get the new surrogate. So S2 is the surrogate of X2. Now this upper bar I'm denoting rounding. For now, just think about it as literally rounding to an epsilon net, meaning just taking each coordinate and rounding off least significant bits. Later, I'm going to talk a little bit more in more detail about this rounding phase, but it doesn't matter. The point is that if I didn't have this rounding, that this guy and this guy would cancel out, and I would just get my original point back. But because I'm using rounding, then I'm getting a small error, and this is why I only get an approximation of X2, which I call the surrogate. And when I have the next point, x3, also a distance r from x2, again, I'm going to compute the displacement to the previous point, round it with an epsilon net, and get my new surrogate. And note that I'm computing the displacement to the previous surrogate and not the previous actual point, for the simple reason that I want to store the distances from a reference point that I actually know, and I'm going to store the surrogates exactly. And if we have another point x4, just the same, we compute the displacement, we round it, we get our surrogate. So we have a surrogate for each point, and how do we use them to estimate distances? In the obvious way. So it's pretty easy to show that the error between each point and its surrogate, I mean the distance between them, is of the order of epsilon times r, where r is the distance that we have here between consecutive points. So if you want the distance from x2 to x3, I'm just going to give you the distance between surrogate 2 and surrogate 3, and this is going to be an accurate estimate. And finally, the question is how many bits did we spend here? Did the sketch actually become small enough? So each point needs to remember two things. First, who is the previous point from which I kept it as the displacement? And second, what is the rounded displacement? So the identity of a previous point is just a number between 1 to n. It's log n bits. The displacement is an element in an epsilon net. So it's a d-dimensional point where each coordinate is rounded to some number of bits that depends on epsilon. And by dimension reduction, we know that d is just log n, if we ignore epsilon for a second. So the total size is log n plus log n instead of log n times log n. So log n bits per point, which is what we wanted. So this was simple, but this was, of course, a very well-structured example. This is not the general case. Why? Because I very strongly relied on the assumption that the distance between each point and the previous point is the same. It was exactly the same r for the sake of intuition. And maybe it wasn't clear from my presentation why this was so important. So let me show you where things break down if this doesn't happen. So now suppose we have two pairs, x1 and y1 and x2 and y2. Each one of them has internal distances r, and the distance between the pairs is a much bigger, big R. Let's see where things don't work anymore. I start computing my surrogates, the y1 just fine, we have a good surrogate, but then I get to the surrogate of x2, and the distance between the point and its surrogate is of the order of epsilon times r, because this is the distance that I was rounding with the epsilon net. And this distance is way too big to estimate this tiny distance between x2 and y2. So this doesn't work anymore. What can we do about it? Well, one of two things. First, we can simply scale epsilon down to be smaller. We can always pay more bits and get better approximation. And the other thing we can do is that if these pairs are really well separated, so x1, y1 are really far away from x2, y2, big R is much bigger than little r, we can mentally contract them and treat them as single points from the point of view of each other. So it means that if you want the distance from y1 to y2, I'm going to tell you the distance from x1 to x2, because it's almost the same. And here I actually save bits because I forgot information. I forget that x2 and y2 are different points from the point of view of x1 and vice versa. So these are all of the things that are going to go into the general algorithm. And let me show you how they fit together in the general case. So suppose I have this metric space. The first stage is hierarchical clustering. So I start with each point being its own cluster, and then I just merge nearby points and a bit further points, a bit further, maybe nothing to merge, and so on. So this is a simple stage. I just merge things iteratively until all the points are merged into one big cluster, and I have my hierarchical clustering tree. And the second stage is to store each point as the displacement from a nearby point. So there is a pretty technical process of how to choose those previous points, but it's possible. And we are also going to tune the displacement, the precision along each edge exactly to what we need it to be. So like in the previous slide, in the first case, I scaled down epsilon so the estimates are correct. I'm going to do this for each edge. I'm going to choose epsilon to be exactly what I need it to be so that all the estimates that I'm using it for are going to be correct. So this ensures that all my distance estimates are going to be sufficiently accurate because I pay all the bits that I need for that. The question is, did I not pay too much? Did I not blow up the size of the sketch by too much? And the answer is no. So this is the first thing you need to prove here, that even though we pay for each epsilon exactly what we need to pay, we only pay in total log n bits per tree node. And the final stage is to construct isolated clusters. So like in the second stage, in the second case in the previous slide, where we constructed those isolated pairs, suppose I have a very well isolated cluster in my metric space. What does it mean that it's well separated? How does it look in the tree? Well, when I was building the tree, I was looking further and further for neighbors to merge it with, and I couldn't find anyone. So in the tree, it looks like a long path without branches. And what I'm going to do is simply shortcut this path to a single edge that I'm going to call the long edge. And I have also deleted those purple arrows that I had along this path. So this is where I save some bits. I forgot some purple arrows. So again, I'm only going to shortcut paths such that I'm assured that even after I shortcut them, the distance estimates are still going to be correct. So in this case, I only shortcut it if 7 and 8 are indeed pretty much the same point from the point of view of all of the other points. So this ensures that again, my distance estimates are going to be accurate. And the question is, again, did I make the sketch sufficiently small? Did I get the compression that I want? And again, the answer is yes. The second thing you need to show here is that after this compression stage, after shortcutting those long paths, the tree only has a linear number of nodes, Owen nodes. So in total, we have n log n bits for the whole sketch, so log n bits per point, which is what we wanted. So this is the sketch. This is the data structure that we call the relative location tree. And let me show you how we use it for distance estimation. So this is, I'm going to say the distance estimation lemma. It's a little bit technical, but not really. It says that for every pair xi and xj, we can recover from the sketch two surrogates, I and j. And these surrogates depend on the pair. So it's not like xi always has the same surrogate. The surrogate also depends on the point xj that we are comparing it with, that we are measuring the distance to. And this is why I have those ij in the superscript. So for every pair, we have those surrogates, and we also have a mutual reference point z that we don't know, but we know it exists, such that the following holds. Modulo this z, modulo this unknown mutual reference point, surrogate I is a good approximation of xi, proportional to the distance I want to estimate, and surrogate j is a good approximation of xj, again, proportional to the distance that I want to estimate. And then, just by the triangle inequality, we can report the distance between our surrogates as an accurate estimate of the actual distance. So this is how you get the optimal log n bits per point dependence. And the last thing I want to talk about is the optimal dependence on epsilon. Because so far I only talked about n, and I kept suppressing epsilon to the subscript. So let me talk about it very briefly. And here we are going to, oh, wait, I want to give some examples for distance estimation. Okay, so suppose you want to estimate the distance between point 2 and 8 here, then I unfortunately don't have a mutual reference point between 2 and 8 because I deleted those purple arrows. But I do have a mutual reference point between 2 and 7, which is in this case 1. And this is sufficiently good because we said that the only reason I constructed this path was that 7 and 8 are essentially the same point from the point of view of the other points. So I'm going to return the distance from surrogate 2 and surrogate 7. And but if you want the distance from 7 to 8, then I have better surrogates. I have a better mutual reference point, which in this case is 7. So I'm going to return the distance between surrogate 7 and surrogate 8. Okay, so this is for distance estimation. And as I said, let me talk briefly about the optimal dependence on epsilon. And here we are going to need to use randomization. So far, the whole algorithm has been deterministic. And let me give the intuition of why randomization is going to help us save some bits here. So what was the point in surrogates? The point was that I took some point y, I rounded it to an epsilon close point y tilde, which I call the surrogates, at the surrogate, and then I could use the distance from x to the surrogate as a proxy for the true distance that I want to estimate. But if I am going to make my sketch randomized, then I can design a distribution over surrogates. So now the surrogate tilde y is a random variable, and do just the same. I'm going to use the distance to the surrogate as a proxy to the true distance. And the reason it helps is that I can design this distribution so it's an unbiased estimator of the true point. Whereas in the deterministic case, if you think about y tilde as a degenerate distribution over surrogates, which is supported just on one point, it's a biased estimator of the true point y, and this is why it is lossy, and randomization is going to help us avoid that. So just to wrap up the description of the algorithm, let me state the actual distance estimation lemma for the Euclidean case. It is very similar to the previous one, but a bit different. So again, I have these two, for every 2 points xi and xj, I have these two surrogates, surrogate I and surrogate j. This time they are random variables. And I also have this mutual reference point z that we don't know, such that modulo this z that we don't know, xi is an unbiased estimator, sorry, surrogate I is an unbiased estimator of xi. And similarly, surrogate j is an unbiased estimator of xj. And each one of them has independent coordinates with support length proportional to the distance that I want to estimate. And designing these distributions is the difficult part. We managed to do this relatively recently by combining techniques from several previous papers. Some are on, some not. But once you have these distributions, then you can use the fact, instead of triangle inequality, we can use the fact that Euclidean spaces have inner products and use this inner product estimator. Here by tilde s, I just mean an identical independent copy of s. And by concentration, this inner product, which is a linear function, is tightly concentrated around the true distance, and I have my accurate distance estimate. Okay, so I think this is all I wanted to say about the description of the algorithm. And the final thing I want to say about metric compression is to loop back to the practical aspect. So if we look at this imaginary axis of bits per point, we started with the dimension reduction, the classic technique that had log squared n bits per point. And this is also a practical algorithm. Dimension reduction is definitely useful in practice and widely used in practice. And then we improved it to the optimal bound of log n bits per point. And maybe you got the sense that this algorithm is maybe not exactly practical. It doesn't look like something you would want to implement. It's a bit complicated because to get the optimal bound, you need to do some complicated things. But nonetheless, we also presented a version of our algorithm, which is simplified. It uses the same ideas, but in a simplified way. And this simplicity costs you. So we don't get the optimal bound anymore. We get log n times log n bits per point, still better than dimension reduction. But the upside is that we get a practical algorithm that you can actually implement, and we have done it. So here you see a comparison of our algorithm in red to product quantization. So product quantization is the prototypical algorithm from the applied literature that I mentioned earlier. It is a very famous paper and a very good algorithm, and also to a baseline of naive rounding, which is exactly what it sounds like. You just round off the significant bits from each coordinate. And here you can see the comparison. So the x-axis is the size of the sketch, the number of bits per coordinate, and the y-axis is the accuracy for nearest neighbor search. This is MNIST. You can see that on the lower accuracy regime, we do slightly worse than product quantization, and we do better on the high accuracy regime. And this approach, this phenomenon is even more expressed on SIFT, which is the standard benchmark dataset for product quantization type algorithms. This is the dataset from the original paper. We do a bit worse on the low accuracy regime and a bit better on the high accuracy regime. And this sort of makes sense to me because this whole formalization that we use of 1 plus minus epsilon is geared toward the high accuracy regime. But ultimately, product quantization, even though it's a very good algorithm and it really gives you good results, it is ultimately a heuristic algorithm, which means that there is a data set that makes it fail. So we went ahead and constructed it, and this turned out to be pretty simple. So the data set is when all the points are organized on one big line. So it's just a one-dimensional data set, but we hide this line in a high-dimensional space such that it's not aligned with any of the x's. And this is why we call the data set diagonal. And as you can see, product quantization is having a certain difficulty, naive rounding is not even wrong, and our algorithm does pretty much as well as it did on the previous datasets. Okay, so I think this is all I wanted to say about metric compression. Let me quickly conclude it. We have the optimal compression bounds for Euclidean metric spaces, also for general metric spaces and L1 spaces that I didn't mention, but they are also an important family. We have the smallest known data structure for nearest neighbor search in Euclidean spaces. And we show that compression is possible beyond dimension reduction in a principled way. And we have a practical variant of our algorithm, which is competitive with the state-of-the-art heuristic algorithms.